Jumps, I have this person at the top of a bridge. It's about to jump off of the bridge, and then you can see as we're going to progress along here, the person's going to fall, and then not hopefully touch the water at the bottom as it should be. You know, we don't want to hit the water. Water's very dense, you'll probably snap your neck or something like that. Okay, so like there's a safety concern, and if you go bungee jumping over a body of water and people haven't thought about the safety concerns, you don't want to hit the water. That's a bad decision. Anyway, for this bridge, we're going to make it a nice, easy value to deal with. We'll make it be 100 meters tall, which is actually a really high bridge. So this is a bridge that's over a fairly decent sized gorge. And as the bungee cord just sits there, before the person ties themselves on and does their little jump, the bungee cord sits slack with an X naught value of 15.0 meters. Again, pretty long bungee cord. As this person jumps, they're gonna fall down to a point 20 meters below the bridge when they get to this part of the story, 20 meters below the top of the bridge. And at this point in time, we'll call it point B. You know, let's label these things. Let's say point A is before the person jumps, point B is when she's part way down, 20 meters below the top of the bridge. When the person's 20 meters below the top of the bridge, in terms of our delta X values, what's the delta X value going to be? 5 meters. And so this is something we could be thinking about as we're telling our story. 5.00 meters. Which means that when she's at this height, how far is she above the ground? Falling 20 meters. What is it? 80, yeah. So I'm keeping track of information here as we go. I'm just telling a story, and she gets to a height of, I'm guessing, you're doing in your head 100 minus 20, 80 meters. Okay? 100, I'll put units in, sorry. Okay? And so when she gets to the very bottom, let's just say this is going to be her lowest point, she is going to have a height. I'll call it height C. We'll call this times C. We could have height B. We can even have delta XB. And when she's at height C, I don't actually know what that value is yet. I haven't figured that one out yet, but I do know that based on what the slack length of the rope or the bungee cord is, she would have gotten to a delta XC value. And what I want to claim is that when she gets to this point, her velocity is 0. She bottoms out. Okay? So that's one thing I could say about this point, is that as a critical point, her velocity is going to be 0. So maybe I'll just say VC is equal to 0 meters per second. That's kind of what I can say about that one. Of course, I'm talking about her speed being 0 meters per second. If I'm thinking about energy and energy conservation, which energy is that one going to be connected to? Yeah? Kinetic, yeah. Yeah, so we're thinking about values related to kinetic energy, gravitational potential energy, and elastic potential energy. So all these three different energies are kind of working together, right? So that's the complexity of the bungee cord problem, is that we have a person at different snapshots in time, but we're conserving not just 2 types of mechanical energy like we were in the past, we're talking about 3 types of mechanical energy. And of course, we're not even talking about things like vibrational energy or rotational energy or any of that. We're just trying to build up and say, hey, look, we can deal with more than just 2 types of energy simultaneously. For this particular bungee cord, I want to give a K value. And let's just say that we've done an experiment to figure out its K value. We've applied a variety of forces. We figured out what the force versus stretch length is and the slope of that graph. And we found it to be 70 newtons per meter. And we say that the mass of this person is 75.0 kilograms. And let's just say that here, where we do this little bungee jump, let's call the acceleration due to gravity, the acceleration in the y direction, 9.81 meters per second squared. All right, so we've got some critical points. And while we have like maybe a more, I won't say photorealistic illustration here, I mean, this is from what really is a nice painting we kind of cobbled together in Photoshop. Over here we've got a more cartoony view. And if you were going to draw something for a problem like this, more of like a stick person drawing would be a really good thing to do. So this is like my stand-in for a stick person drawing, just so that it's all ready for you guys to go. But we've got some different critical points. Point 1, 2, 3, and 4. And I just want to talk about what's happening at these points. So at point 1, this is the no jump. Haven't left the bridge yet. You can see they're just sitting there contemplating what's going to happen next, okay? And then at position 2, this would be a critical point where you've jumped, but no stretch. In other words, the bungee cord has not started to stretch yet. You haven't hit the end of the slack. Or we could even say just at the end of the slack. We've just gotten to the point where we hit the end of the rope. Okay? This one here, we could say stretched but still falling. Actually, you know what? I don't even want to put the label there because I want to reserve a little bit of white space. I would like to reserve a little bit of white space. Yes, sir. Jump, but... Oh yes, thank you. Jump, but no stretch. You're right. Thank you for hearing what I said, not just what I wrote. I appreciate that. Thanks, Will. This one here, it's stretched, but still falling. And then this one here, important point, is the lowest point. And at the lowest point, we have maximum stretch. And V is equal to 0 meters per second. So the reason I wanted to leave myself a little bit of white space is because I want to sketch out some equations for this too. Because each of these points, call them point 1, 2, and 3, there's some overlap with positions A, B, and C. A, B, and C are going to be for my problem set, but 1, 2, and 3 are some nice points to keep in mind for any old jump. I could come up with an equation for scenario 1. For scenario 1, if I was going to calculate E total for position 1, or scenario 1, would be EG1 plus EK1 plus let's call it spring energy, S1. And actually, that's what we're going to claim is the starting position or the starting energy for each of these. So you know what? Maybe I'll just go through and do that for each of them. E total 2 is EG2 plus EK2 plus ES2. And the same thing for 3 and 4, only with 3s and 4s in the subscripts. I want to start thinking about how I could simplify each of these expressions, and by that I mean which things could I zero out? Which things are just automatically going to drop out because there's values that are 0? So let's look at the first equation. Are there any of those energies in the first equation that are going to end up being 0? You haven't jumped yet. You're just sitting on a bridge, cross-legged. Yep. EK1's gone. Yep. Haven't started falling yet. Yeah. You're right. ES1 would also be gone. So those guys are going to be 0. That's nice. You know what? And the nice thing about that is when you're just sitting there on the top of the bridge, you've already got all the energy you're going to have, right? You've stored the energy just by getting to the top of the bridge. Makes sense. It's a kind of energy storage. Position 2. I'm part way down, but I haven't stretched the bungee cord yet. Can anything go to 0 on this one? Yeah. Still yes. Anything else? No, it doesn't seem like it. In fact, you're falling, so you're going to have some kinetic energy, and you're still going to be above the ground. Audrey? Right. So like when you get to the point where you've jumped, but it hasn't stretched yet, that's when you've fallen just to the height where you've gotten to the point where the bungee cord is taut, but not stretched at all. It hasn't been distorted yet. Well, I guess if you're standing on the bridge, you could measure how long your bungee cord is, and it wouldn't have been stretched at that point because it's just slack with no weight on it, right? And so you could measure that bungee. I mean, we're in like this hypothetical situation. You're standing on a bridge, you have a pile of bungee cord in front of you, and you could sit there and measure this thing out with a meter stick or a trundle wheel or a measuring tape or whatever. That would be your X naught value. And that's how far below the bridge you are at position 2.
But on a test, you tell us?
Yes, on a test I would tell you, yes. But in the real world, if you decide to jump off a bridge and do some physics at the same time, okay? All right, equation 3. Anything I can zero out here? Sadly, no. Look at this. You're gonna be above the ground. You're gonna be falling still. You haven't come to a stop, and the bungee cord is stretched, so nothing zeroes out. What about 4? Yes, sir. EK. Yeah, you come to a stop at the bottom, right? That's the basic idea, is that V is equal to 0. So EK disappears, and there are always going to be some people that say, well, could we just make EG4 be 0? Look at this. Look at our more detailed illustration. Assuming you don't want to snap your neck when you hit the water, because that's what's going to go first, right? You don't want the final height to be 0. You really don't want that EG to be 0. That would be bad. Okay, so we're going to keep it a non-zero value. So those are our kind of guiding equations, if you like. And I want to use those guiding equations to talk about how we're going to solve this problem. So we've got an illustration for our specific scenario. We have guiding equations for sort of the general case of falling off a bridge with a bungee cord around your ankles. I want to look at this question. What will her speed be when she has fallen 20 meters if the elastic coefficient of the cord is such and her mass is such? The bridge is 100 meters above the water and the unstretched length of the cord is 15 meters. Assume this is a 100% efficient drop. When I say it's a 100% efficient drop, that means that we don't have to, in addition to all this, deal with percent efficiency, okay? Recognizing that obviously drag is a thing. So if we wanted to level this up in terms of complexity or realism, we have to throw that on top of it as well. Talk about percent efficiency from one point to the other, which we've done with roller coasters. So this isn't something that should be like beyond us, but we're not doing it right now. All right, so what's her speed going to be? Let's take a look at actually maybe I should bring those equations in view. Which equation should I use? 1, 2, 3, or 4? What do you like, Will? 3, okay. What's another one I should use? 3, remember, is when she's gone beyond the stretch of her slack cord. Has she gotten beyond the stretch of her slack cord, or is she just at the end of her slack cord on this one? Let's read it again. The bridge is 100 meters above the water. Unstretched length is 15 meters. She'll be when she's fallen 20 meters. Has she stretched the elastic yet? Seems so, okay. So then we got position A, we've got position B. Position A, we're talking ET1 equals, and I'm just going to call it, sorry, I'll get on screen. ET1 isn't 1 for the equation over here. We're just going to call it ET1 because it's the first position. ET1 equals EG1 plus EK1 plus ES1. At position B, this is actually scenario 3, but we're going to call it, well, you know, why not? Let's call it ET3. What the heck? Just to be consistent with the equations above. ET3 is equal to EG3 plus EK3 plus ES3. We could have called it EG2, EK2, and ES2, but I'm going to try and be consistent with those guiding equations up above. And what we've already said is that for scenario A, these guys are gone. And if we're going to claim conservation of energy, then what we're going to be saying is that E total 1 is equal to E total 3. That means that we can set each of these guys equal to each other, and we can say EG3 plus EK3 plus ES3 equals EG1. And what are we trying to find again? We're trying to find her speed. So we're trying to get kinetic energy 3 all by itself. So EK3 equals EG1 minus EG3 minus ES3. We can expand this thing out. We can say, all right, well, that means that EG1 is mass times acceleration due to gravity times height 1. mass times acceleration due to gravity times height 3 minus, remember the energy equation for spring energy, oh, I'm sorry I was off screen, is 1/2 k delta x 3 squared. EK3 is going to be 1/2 mv3 squared. And I'd really like to get that V3 all by itself, so I'm fighting calculating the kinetic energy and then subbing it into a kinetic energy equation to solve for V3. I think I'd like to do it all in one go, just because I want to be a little bit more mature about things. So I'm going to take this guy up and isolate for V3. I'm going to say V3 is equal to, and when I take that 1/2 over to the other side, it'll be 2 times all that stuff that was already on the right-hand side. Divided by the mass, square root the whole thing. I'm really not sure how much I want to cancel out here. Can you see that I can't just eliminate the m because there's not an m in the final term? So sadly, I actually have to sub all this stuff in. Before I think about subbing everything in, I feel like up at the top of the page here, I know mass, I know k, I know ag. I want to make sure that I really know all my other values. It looks like 100 is my H1 value, so I have that one. Do I have the H3 value? Does the story tell us anything about the H3 value? Look at this. She's fallen 20 meters. Isn't that scenario B that we kind of defined earlier? And by subtraction, we said that that means that H3 must be 80 meters, right? So that's our 80 meters. I know it was scenario B up at the top when we were first defining the question, but right now it's going to stand in as our H3 value. So yeah, all of our givens are present. I'm going to move my VB just over the other side just to buy myself a little bit more space and start subbing in my values. 2 times, oh my goodness, this is a lot. Make sure that I can make my multiplication signs and my minus signs look different. What's our delta x value? We fell 20 meters. Aren't we 5 meters below slack now? Okay. And if you're wondering where that 5 is coming from, look back to the picture. She's fallen 20 meters. The slack length was 15 meters. Delta x is going to be 5 meters. Okay, just in case you missed that. Divided by her mass, 75 kilograms. Let's cap that off. And square root, don't forget to square root the whole darn thing. You guys tell me, make sure you can get it all in. When I went and calculated this earlier, I ended up getting 19.211 meters per second. Is there anybody, you got it? All right, thank you, Peyton. All right, so approximately, oh, how many sig figs do we have here? 3, it looks like. So about 19.2 meters per second. And that's pretty fast. But really, like, I mean, this is a little bit of bookkeeping. We're keeping track of critical points and pulling it all together. 3 different types of energy being conserved. The next question is, how far above the ground is she when she stops? Well, again, we're just cherry picking out our guiding equations, right? So when we look at our guiding equations, we're talking about what's going to happen, our illustration at the top of the page, when she comes to a stop, we're talking about comparing what happened at position A to what happened at what we defined as position C. At position A, we had an E total 1 equals EG1 plus EK1 plus ES1. And what we'd said was that the kinetic energy and the elastic potential energy were gone because the bungee cord wasn't stretched and she hadn't started falling yet. And the E total at position C, I should go back up to my guiding equations. Which one are we looking at? 1, 2, 3, or 4? Must be 4, right? She's gotten to the bottom. She's bottomed out. So I'll come back down here. And just to be consistent with those guiding equations, I'll call it ET4, although most people would probably call it ET2, just because we're comparing before and afters, or ET initial and ET final, or something along those lines. But we'll just call it EG4 to be consistent with those indices at the top of the page. So EG4 plus EK4 plus ES4. And what we had said is that at the bottom, she's going to come to a stop at her lowest point. It's actually going to be the maximization of the ES4, or the ES, I should say. It'll be the minimization of the EG4, so max-min problems, I guess. I want to do a little bit of side figuring, though, because I can sort of predict that at some point I'm going to have to deal with the delta X value for ES4. You guys can see that, right? And if I take a look up at the top of the page, I'll go there in just a minute, but you have it in front of you. If I have a total height for my cliff of 100 meters, I know that the slack length, X naught, plus delta X C plus HC, X naught, delta X C, and HC should all add up to 100. And if you want to just like have a visual on that, I'll pan up and then I'll pan back down again. HC, delta X, and then the distance below the bridge is the X naught value. Okay, so those three things should add up, like just spatially, that makes sense. So I'm not driving anything like ground shaking here by saying something like that. But the reason that I'd like to say it is that we want to know how far away she is from the bottom of the cliff. Unfortunately, when I look at this expression, there are two unknowns and it's only one equation. That's okay, we can roll with that. We're not going to shy away from it. So we say 100 meters equals X naught is 15 meters plus delta XC plus HC. And as I do a little bit of isolating, that means that I can get all the numbers onto one side. And I could write delta XC in terms of HC. Now, I'll tell you why that would be useful later, okay? So delta XC could be written as 100 minus 15, 85. Take the HC over to the other side, 85 minus HC. Okay? Now, I want to put a box around that. And I want to put it in my back pocket for later as equation 1. So it's a binomial that I'm going to hold on to for later. And then I say, okay, well, what we're really trying to get at here is conservation of energy. So we'd say ET1 is equal to ET4, before and after for a 100% efficient system. And if I expand EG1 and ET1 and ET4 out, then I get EG1 equals, ET4 is EG4 plus ES4, and that seems innocent enough. So then I can expand that out, and I can say, okay, well, I'll start over here on the left-hand side. MAG H1 equals MAG H4. Hey, you know what I should do? I know I called it delta XC and HC. Because I'm using indices of 1s and 4s here, are you guys okay if I turn that C into a 4? We'll turn this C over here into a 4, because that'll keep all of our indices matched. Okay? Same idea. Plus 1/2 K delta X 4 squared. And now I'm like, ooh, this is getting interesting. I've got an H4 and a delta X4, just like I have an H4 and a delta X4 up here. And so this is actually kind of useful for me. I'm thinking now I have a system of two equations with two unknowns. And that's something that I do feel familiar with. Yep.
The equation for the spring,
Yep.
like, do we have that on the equation sheet? Are we supposed to know, like,
Well,
M to K and then V to delta?
yeah, so elastic potential energy for a spring, you should know that one, yeah. Yeah, it has a similar format to kinetic energy, 1/2 mv squared, but it comes, from a different place. It has to do with the ideal spring. Yeah. Yeah, so 1/2 K delta X squared is an equation for energy that you should know. And we could call this equation 2. I'm cool with calling it equation 2. But what we're really going to do with this thing is sub in equation 1. And if we're going to sub in equation 1, that means taking that binomial. I'll put a little underline under the binomial here and talk about where it's going to go in. That's delta x4. And the only place that it has to go in is into this little spot right here. Okay, so that little orange squiggle is going to go into the place of that other little orange squiggle. That's our substitution. And so we get, I'm going to butt right up against my left-hand margin. MAGH1 equals MAGH4 plus, that means I get this whole equation. The only thing that I won't know in this whole equation is H4, and that's kind of nice. 1/2 K times, instead of delta X4, I'm going to write the brackets, 85 meters. I'll just leave that meters in there, minus H4 squared. Unfortunately, those of us that are really into recognizing what happens with binomials, when you square them, they turn into what dreaded thing? It rhymes with dadratic. Not quite. Quadratic, yeah. Okay, so it's gonna expand out. So sad. So just in case there's people that don't believe what I say, not that I'm a liar, I just want to make sure that it's really clear. If I have 85, I'll drop the units, okay? 85 minus H4, you can drop the units too for this one. 85 minus H4. We're gonna be multiplying those binomials together, and you might have had a teacher that used the short form foiling, first outside, inside, last, binomial times binomial. That's what we're doing here, okay? So it didn't go away. I don't know how many years ago we learned that, but it hasn't gone away. And if we do that, you know, I've done the legwork because I don't really want to teach a lesson on how to foil. I've done a little bit of legwork here just to say that I would get an embedded quadratic that looks like this, plus 1/2 K, and then what we just did with the foiling there would end up being coefficients 7,225. I'm dropping the units. I'm conscious of that, okay? I'm just trying to show the coefficients. 170 HC. Oh, sorry, I called it H4, didn't I? Plus H4 squared, and then close the brackets. So that binomial product ends up being everything that I just put inside of orange brackets. And when we look at this, the first question that we did today seemed like, okay, I can keep track of a little bit of extra bookkeeping. This one's all the bookkeeping from the first problem, plus you throw quadratics in there as well, okay? So it's, again, not mathematically beyond us, but it does require us to be organized, which is why I wanted to make sure that I had a separate little mini lesson just for this problem type, right? Like, people struggle with this. It's really just a system of two equations, but sadly, it's not a system of two linear equations. Only one of the equations is linear. The other one is a quadratic. So that's kind of annoying for a lot of people. Anyway, if I go through this process and expand it out by subbing in the numbers, that's what I want to do next. And I will say it again, I am dropping out the units. I'm just going to write the numbers, mainly because we'll run out of space otherwise. So this is one of those super rare situations where I'm not writing the units. I always like to write the units. So let's do it. 75 kilograms, I'm just subbing in for the mass, times 9.81 meters per second squared times H1, 100 meters, equals, on the other side, 75 kilograms times 9.81 meters per second squared. It's a 9.81 times H2, because I don't, or sorry, H4, because I don't know what H4 is, plus 1/2, the K was 70 newtons per meter, times this quadratic that we just expanded out. And I'm going to have to pan over. So 7,225 minus 170 H4 plus H4 squared. Close bracket. And again, this really highlights that the only thing we don't know right now is H4, or the height at the very, very bottomest. And if I wanted to collect all these terms together, I can do a little bit of math, and 75 times 9.81 times 100 is 73,575. I said I did the legwork beforehand because I trust that we can do that multiplication. It's just a 3-term multiplication. Equals Again, I did the legwork beforehand, 735.75 H4 plus 1/2 of 70 is 35. Open bracket, and we still got 7,225 minus 170 H4. And yeah, I'm taking a little bit slow here because I want everybody to see what's going on in the brains. And then we're going to distribute through that bracket. And I recognize that you could have probably done this whole step in your calculator all in one go, but we're going to do it kind of stepwise just to make sure that everyone sees what's going on. 73,575 equals 735.75 H4 plus 35 times 7,225 is 252,875 minus 35 times 170 is 5,950 H4 plus 35 H4 squared. I'm fast forwarding things. I know we could do all that stuff on our calculators. And then I'm going to ask the room, what should I do next? Yeah? Yeah. I love it. Collect all the like terms. So what I'm going to do is I'm going to underline the terms that are alike in the same way. So see this wavy line? Those two values are like terms. I have to collect those two together. I want to double underline this one, and I'll double underline this one to make it clear that those two are like terms. I have to collect those two together. And there's only one H4 squared term, so it's a one of a kind, I guess, in that way. And what the man says is leave a 0 behind on the left-hand side, which in this case means I only have to take one term over. So I'm going to collect them. I'll say 252,000. I am actually going to write them out again because, again, I want to make sure that there's nobody who's wondering what's being done here. 252,875 minus 73,575 plus 735.75 H4 minus 5,950 H4 plus 35 H4 squared. And then, of course, now that we've collected our like terms, we're going to simplify yet again because we've got these guys subtracting, we've got these guys subtracting, and that's going to generate finally some consolidated coefficients, which sounds like an amazing 90s indie band. The consolidated coefficients. I'd go see that group. No, I wouldn't. Anyway, yes, I would. I don't know. I'm so on the fence about this. So binomial about it. 179,300 minus 5,214.25. And can you guys fact check me on this one? I know there's some people doing the calculations. Are there other people that are getting these coefficients? Beauty. Okay. I heard the calculators going, so I figured. And then plus 35 H4 squared. And then finally, I mean, it seems like after a lot, we have like a quadratic that we could hand to somebody that's like years younger than us, right? It's just that we had to get to this point. And that's something that I think is kind of the achievement here. And if I wanted to underline this thing and make sure that we really get the coefficients to pop for us, if this is standard form for a quadratic, I don't want to rewrite it again. Can we just say that this is coefficient A? This is coefficient, including the negative sign, coefficient B, and this guy here is coefficient C. And if we're going to go through and we're going to throw this into a quadratic formula, what we're saying is that H4 is equal to, and some of you have fancy calculators, but remember, formula for quadratic is negative b plus or minus the square root of, and I think like when I was a kid, we almost turned this into like a song. I think that we had a chant, but negative plus or minus b squared minus 4ac all over what? 2a, yeah. So if you can't just like quote that off like it's like some sort of, I don't know, like prophetic thing or something, then you haven't really lived the math. Okay? We can sub in the values. And if you have a fancier calculator than I, then you can probably just put in your A, B, and C values and it'll smartly tell you the answer, but I'm going to write it out anyway. 5,214.5 plus or minus the square root of, oh my gosh, 5,214 point, oh no, was it 0.25?
Yeah.
Oh, you guys, I almost messed up. 0.25 squared minus 4 times 35 times, can you see why I dropped out the units? Times 179,300. Let's extend that square root a little bit further. And I don't need that school logo in there. Divided by, yay branding. 2 times A, gosh, what was A again? 35? And I can't believe that I've totally painted myself into a corner here. Does anybody have a real smart calculator that's got the answer? Did you get it, Brian? Well, I don't know if it's right either. What'd you get?
For under the square root?
Yeah. No, like as the total answer.
There could be 2 different answers.
Yeah, it gives me 2 different answers. If it makes you feel better, one of them starts with a 9 and one starts with a 5.
First one I have is 95.1.
Okay, so we could say H4 equals, what did you say, 95 point what? 124? Okay. Or what's the other root? Yep. 53.854. Now, you know, in math class, we often will just say, oh, well, those are the 2 possible answers. And we could round it off to 3 significant figures. But one of those is admissible, and one of them is not admissible in this physical system. In this physical system, it's a real system, which we described at the top of the page. I could say, oh, well, the final height is 95 meters above the ground, or the final height is 53 meters above the ground. Let's take a look back at the original scenario. The cliff itself is 100 meters high. Did she stop 95 meters above the ground? Why? Yeah, she's at 85 meters when she hits the end of the slack. That would mean that she magically stopped before she even hit the end of the bungee cord. That doesn't make sense, therefore inadmissible. Okay? So we can mathematically solve something, but we're going back to the reality of things and deciding what's admissible. She's not just staying suspended having never stretched the bungee cord. She must be 53 meters above the ground. That makes total sense. And you know, what's more, I can highlight that as the answer. We can say, yes, she lands 53.9 meters above the ground. This is not admissible. 53.9 meters above the ground. And we can explain why it's not admissible, but I've run out of space on my page, but I've said it out loud. But once I have this H4 value, somebody else might come along and in part C of this problem, which we're not going to do because I don't want to say it's beneath us, but it's really easy. You could say, how much did she stretch her bungee cord when she got to that height? Well, if she's 53.9 meters above the ground, can't I go back up to equation 1 and figure out how much she stretched her bungee cord by? Bada boom, bada bing. We're done. Okay? But that's a real thing. And I wouldn't leave that up to inspiration for people. That's why we're kind of doing it together, right? Like, that's a lot. I love that question. And there's a lot of people online that talk about this one.